Welcome to this lesson about two important things in data analysis and in statistics. The law of the large numbers and the central limit theorem. We start today with the law of large number, and I'm going to give you the informal theorem, or informal law. I put here informal. And what is the law of the large number? The mean of a large number of realizations of a random variable, I will denote R dot P, converge to the expected value. Random variable big X converge to the expected value of the random variable. So this is one justification why the expected value is very important. There are other reasons why the expected value is very important. This is one of them. I will give you one example in the context of casino games. When you go to a casino, the result in the games that you play, the results are random variables. But the expected value of those random variables, the expected values are negative for the players and positive for the casino. Because casino is a business that they want to make money, so they want to deal with positive random variables. I will give you here one example. It's, the first exercise in the group of exercises about this topic, and I will put here this first example. I will consider a game in a casino, and the result of the game is a random variable. So big X is the result of a game in a casino. And I will give you the probability function. And this game is very simple. The player, he has a probability equal to 0.6, a probability of a result equal to minus 5, and a probability equal to 0.4 of a result equal to 5, and 0 other values. So we look to this probability function, and it's easy to understand that the game is not favorable to the player, because he has more probability of losing than winning. But that is what happens with all games in casinos. Even with poker, the casino, part of the money goes to the casino, and only part goes to the players. So the expected value when you are playing poker is always negative. So But here the game is very simple, and what is my question? My question here is, I will put here a name of some person, I will put Aniceto will play, let me see, 200 times, 200 times. Aniceto will play 200 times. And now my question is, what is the final result? What is an approximation for the final result using the law of large numbers? So the question is, what is an approximation for the final result using the law of large numbers? Using the law of large numbers. Now I'm putting how we solve this exercise. Okay, I put here, this is a question. I want an approximation for the final result. So, what is the final result? The final result is the sum of 200 random variables with this probability function. So, I will clean here this part. We already know what is the random variable. This is the probability behavior for each game, but he will play 200 games. So, what is the final result? The final result is equal to small x1 plus small x2 until small x 200. I'm putting here small x because I'm talking about the observed value of this random variable. So the observed values, for the observed values, we use the small letters. So the final result is the sum. But what we know about the law of large numbers? We know that the mean of a large number of realizations, the mean converges to the expected value. So the first thing I need to do now is to calculate the expected value of this random variable. And that is very easy. We already know how to do it. We need to multiply each possible value by the probability. So the expected value for this game is what? Is probability of minus 5 times minus 5. 0.6 times minus 5. Plus probability of 5 times 5. So 0.4 times 5. So, and the result is easy. Here we get minus 3 and here 2. The final result is minus 1. So the expected value for this game is negative and equal to minus 1. And now what we know about the law of large numbers. Using the law of large numbers, we know that the mean, small x bar, will be near the expected value when the number of realizations is big or is large. Here we have n equal to 200, and I will consider this a large number. So n 200 is a large number. And so what we have? We have that the mean of the realizations will be near the expected value. And now, what is the mean? What is the mean? The mean is the sum divided by n. So is the x1 plus x2 plus xn divided by n. And we know by the law of the large number that this is near the expected value. And now we can solve the problem because we have here the expected value. And this part here is the final result of the player. So this part is the final result. And now it's easy because I know the expected value, I know the number of realizations, 200. So here the sum, that is the final result, divided by 200 will be near minus 1, and the final result will be near minus 1 times 200 will be near minus 200. Okay? So, what we are saying with this, that the player will have a loss near 200 euros if he will play 200 times the game. Okay? And if he wants to play 1000, if you want to play 1000, the n will be 1000, and he will get a loss near 1000 euros. So, and this is very simple example, but this is what happened with all games in casino. So, all players that are addicted to casino games, all players will lose a lot of money. No player will win if they play a lot casino games. But we can use this law in our favor. How we can use this law in our favor? We can choose games with positive expected values. And what are the games with positive expected values? There are many. For example, when we are investing in companies, the expected value can be positive because many companies, they produce value to the customers, to the society, and because of that the prices will raise, and the expected value of many companies, of the returns in many companies, the expected values are positive. So what is a lesson that you can learn with the law of large numbers? The lesson is don't play games with negative expected values, but instead play games with positive expected values. When we are dealing with investments, we try to play games with positive expected value. So now we will move on to the central limit theorem, the most important theorem in mathematics. Because many random variables, we know the probability behavior because of the central limit theorem. So, central limit theorem. I will denote by CLT. And I will give an informal statement, so informal. And what is the idea behind the central limit theorem? The idea is that the sum of random variables converge to the normal distribution. So I will put here this way. Let's consider that I will give the theorem only for independent and with the same distribution random variables. So let's consider big X, big X1, big X2 until big Xn. Random variables, or let me put before independent random variables with the same distribution. With the same distribution. That can be any distribution, uniform, binomial, Bernoulli, any, with the same distribution. And if they have the same distribution, they have the same expected value and the same variance. But I will use that later. Then, the sum of a large number, I will put this, big X1 plus big X2 plus big Xn, and I will denote this by Sn, the sum of n random variables that are independent and with the same distribution. This sum will converge to the normal distribution. The meaning of this point here is near or approximately and not exactly normal. It's not exact. It converges to the normal distribution when n is large. So when n is large. But what is n large? In practice, we can have n large with n equal to 4 or 5. Some distributions, when we had 4 or 5 random variables, we get a distribution very close to the normal distribution. But in practice, we consider large. In practice, we will consider 30. So 30 is not too much. In practice, what is large? In practice, n equal or higher than 30. So, this is one reason when you are doing, for example, marketing research, we try to use at least a sample with the dimension equal to 30. Okay. Any study that you do with data analysis is very useful to use at least a sample with 30. But we are living in a world with every day more data, and now have samples equal to 30 or higher is very easy. Now it's rare to deal with samples with less than 30. But now let's apply this most important theorem of mathematics. Let's apply it in one very simple example. So I will clean here the theorem and I will put one exercise. Exercise number 2. But now for the central limit theorem. I will put this way. Aniceto, this is a strange name, but I will put this Aniceto. Today we'll play 81 times. The previous the game of exercise 1, and the game of exercise 1. And now, what is the question? Using the central limit theorem, what is the probability that he will lose money? So, using the central limit theorem, calculate the probability that Aniceto will lose money. So how we do this calculation? How we solve the problem? What is the probability that the Aniceto will lose money? He will lose money if the sum of the 81 games, if the sum is lower than 0. So, what is the final result? Final result of Aniceto. The final result. Now I will put in terms of a random variable. Final result is a random variable that is equal to a sum, okay? Because final result is the sum of 81 games. Alguma dúvida aí? Se tiver dúvidas, podem interromper, tá bem? Não tenham problemas. Final result. Final result is what? Is the sum of 81 games. So it's big X1 plus big X81. This is the final result. And lose money. What is lose money? Lose money is the final result lower than 0. So probability that he will lose money, probability of lose money is equal to probability that the sum is lower than 0. Okay? And now, what we know by the central limit theorem, we are summing 81 random variables, more than 30, and by the central limit theorem, when we sum more than 30, the sum converges to a normal distribution. So we know by the central limit theorem that the sum of 81 is very near a normal distribution, Why? Because of the central limit theorem. Central limit theorem. Here we have what? We have the n higher or equal to 30 because our n is 81. Okay, our n is 81. And now what I need? I have here a random variable that is very near the normal distribution. And what I need to do? How I calculate the probabilities with the normal distribution? We need to do the standardization. Now it's the previous number 4 group of exercises. We have done some exercises with the normal distribution. Now I will clean here the question, and I need to do the standardization. And what is the standardization? Is the we need to subtract the expected value and divide by the standard deviation. So standardization. Recall from if we have here big Y that is normal. Big Y that is normal. Normal with parameters mu and sigma. And here mu is the expected value and sigma is the standard deviation. If we subtract the expected value and if we divide by the standard deviation, what we get? If we have a normal, with the standardization, we get the big Z that is what? Is the standard normal. And we have a table for the standard normal distribution. And we have a table with accumulated probabilities between 0 and 3.09. And we can now calculate any probability for the big Z. But what we do with other normal? With other normal, we do the standardization to get the Z. Then we can calculate the probabilities. And here we are going to do that. We need to do the standardization. But to standardize, I need the expected value and I need the variance. So first, I will do that. But we have random variables with the same distribution and independent. We have big X1, big X2, until big Xn with the same distribution. So if they have the same distribution, then they have the same expected value and the same variance. Here, for any of the random variables, we have, I will denote the same expected value as mu, and I will denote the same variance equal to sigma squared. But now we need to have a little attention. Why? Because now here the mu is the expected value of each individual random variables. But we want the expected value of the sum because we want to do the standardization for the sum. We have the sum, 81, and now what is the standardization? What is the standardization here for the sum? We need to subtract the expected value of the sum, and we need to divide by the standard deviation of the sum. What is the standard deviation? Is the square root of the variance. Okay. And we know that with the standardization we will get a distribution that is very close to the big Z. Why? Because this one here is very close to the normal, and we are here doing the standardization. If we standardize a normal or a random that is very near the normal, we get a random variable that is very close to the standard normal. But now I need to calculate the expected value of the sum and the variance of the sum. And we know that it's very easy to do it because we need only to apply the simple properties for expected value and variance. We know that the expected value of the sum is n times mu, the individual expected value, and the variance of the sum is equal to n times the individual variance. Okay? So now we need to do what? We already know that we have 81 random variables, so this n is 81. We need to calculate now the individual expected value of each game and the individual variance for each game. But we already have calculated the expected value for each game. It's minus 1. Okay, we already have done that. But I will put here again the probability function of each game, and it is 0.6 probability of minus 5, 0.4 probability of 5, and 0 other values. In our example number 1, we already have calculated the expected value equal to minus 1. Here I will put big X high and here big X high, because now I want to be explicit that we are talking about big X1, big X2 until big Xn. And all of them, they have an expected value equal to what? Equal to minus 1. And now I only need to calculate the variance. But that is easy. The variance for each game is what? I need to use this probability function to calculate the variance. And that is easy. The variance, as we have done in other exercises, is the expected value of x squared minus the expected value squared. And now, I will clean here this part. And now, how we calculate the expected value of x squared is the same way as we have done for the expected value, but we put the possible values squared. So I will multiply minus 5 squared by the probability. So 0.6 times minus 5 squared. And now I will multiply 5 squared by the probability, 0.4 times 5 squared. And this is the expected value of x squared. But I need to subtract here the expected value squared. Expected value is minus 1, so minus 1 squared. And final result is, this part is very easy. We get here 25 minus 1. Minus 1 squared is 1, so the final result for the variance is 24. And now we know that the expected value is 81 times minus 1 for the sum, minus 81. Expected value of the sum of the results from the 81 gains. And the variance is 81 times 24. I will let here 81 times 24. And now we can solve our problem here. Now we have everything to solve our problem, because I wanted the probability that the sum of 81 random variables is lower than 0. And now I will do the standardization, because this one here is very near a normal random variable. And the standardization, what is the standardization? Is I subtract the expected value. I will put here to have more space. The standardization, I subtract the expected value and I divide by the standard deviation. The square root of the variance. I'm putting the expected value, square root of the variance. And I'm doing here the standardization in the first member. I need to do also in the second member. So I'm doing the standardization with the sum and now here with the zeros. 0 minus expected value divided by the standard deviation. And now what we know, because we are doing here the standardization, everything here is near a big Z. And now the problem becomes more easy, because now we have this near probability that Z is lower than. And now I will substitute here the expected value by minus 81. I will substitute here the expected value of the sum. Expected value of the sum is minus 81. So I'll put 0 minus 81. This is the expected value of the sum. And the variance of the sum I have here is 81 times 24. So I'll put square root of 81 times 24. And now what we get? Here we have probability that Z is lower than. I will do here the calculation. I need to calculate that part. See. So I will put only 2 decimal places, because we need to look to the table with only 2 decimal places. So I will put here 1.84. And what is this? This is the big F for the Z. in 1.84 and 1.84. And now I can represent that as an area in a density function. We know that the big Z has a bell shape with the center in 0. But what is the big F 1.84? Is the accumulated probability until 1.84. And it is a probability in an interval. What is the interval? Between minus infinite and 1.84. So it's an area between minus infinite and here, let me put here 1.84. So is this area here? This area is what? This area is equal to the BF 1.84. And now we need to go to the table. Let me clean here. And how we do this? We have 1.84. We divide 1.84 in two parts. The first one is the whole part and the first decimal place, 1.8. And the second part is the second decimal place. And now we go to our table and we check in the first column the table of the standard normal that you have in the Moodle. We check 1.8 in the first column. So here the table starts with 0.0, 0.1, 0.2, but I want what? I want 1.8. So I search here in 1.8, and now the second decimal place is 0.04. And what we do? Now we check in the other columns. Here, the other column, we have 0.0. I don't want 0.00. Then I have 0.01. No, I need to go to 0.04. And now, in the intersection of 1.8 and 0.04, in the intersection we have the accumulated probability. We have this area here that I painted with white, and now I will check the value in the table. In the intersection we have 0.9671. So, and this is the probability of 0.9671. This is the probability that the player, the aniceto, will lose money. So it's probability that he will lose money is very high. So the probability that the sum of the 81 games is lower than 0 is about the 0.9671. You have only around 3% of probability of winning money. So you can see it's a very bad decision. Play 81 times. And if he play more, what will happen? If you play 100, 200, this probability will very fast go very near 1. Very near 1. So you see what happened to players that are addicted to casino games or even online casino games. I don't know if some of you here play, if some of you plays casino games, but if you do that, learn with the law of large numbers and with the central limit theorem that you will lose money and maybe lot of money if you do that very frequently, okay? So, I finish now the main part of today's lesson. So, I gave you the law of large numbers and the central limit theorem, and for each I used a very simple exercises.